Hi there viewer, I am Sarisha Ramjeawon from the University of KwaZulu-Natal, studying my second year in Bachelor of Science in Environmental Science. Today I'll be telling you about not too hot, not too cold. So I guess you're listening to my lecture because you're curious to know what makes Earth the right temperature. Well, guess what? You're listening to the right lecture. Before I go any further, we are going to recap on the previous talk. We learned that you are unique. The universe was formed in the Big Bang, and this is made mostly of hydrogen and helium. Carbon and other heavier elements were made thereafter. The solar constant was formed from debris of an exploding star. Hence, we have carbon, oxygen, and nitrogen elements. Therefore, we can say we are made of stars. So why is planet Earth habitable? For that, we look at a simple idealized model of hierarchy to start us off. This is a diagram which will be very familiar throughout the course. We look at Earth being just a bare rock, and we calculate that Earth will be too cold at minus 18 degrees Celsius. The key concepts will be focused on are albedo, Wien's law, in conjunction with Stefan Boltzmann's law. We calculate effective temperatures, and we look at the habitable zone. Starting off with location, we see that Earth is one of 4 rocky planets, which is about 115 million kilometers away from the Sun. Its solid surface is a favoring factor for habitability. We compare the Goldilocks and Three Bears story to Venus, Earth, and Mars. Looking at this illustration in front of you, Venus can be compared to Papa Bear's porridge, which was too hot. Venus has a surface temperature of 450 degrees Celsius, while Mars can be compared to Mama Bear's porridge, which was too cold, which has a surface temperature of minus 53 degrees Celsius. However, Baby Bear's porridge can be compared to Earth with a just right temperature of 13 degrees Celsius. We can then see that location matters. Looking at this illustration, we have Venus, Earth, and Mars at a given distance away from the Sun, with its temperature on the y-axis. We see that Venus is well above 400, while Mars is below the x-axis and Earth just above it. So let's test the hypothesis like scientists should do. To do this, we calculate the model temperatures. Part A of the practical is how much energy does the Earth receive from the Sun. For that, we look at black body radiation. We look at the absorption and heat emission. A black body absorbs all the radiation incident from all angles and frequencies. The radiation spectrum is dependent on the temperature of the body. Now I know I pretty much lost you along the way. However, let's look at the next slide to grasp this concept better. We look at energy and the solar spectrum. The Sun's spectrum is very similar to a black body. But what is a black body? So let's compare this. Your grandmom or mom told you not to wear a black jersey on a hot day. Why? Well, those reasons are very similar to what a black body is. A black body is anything that absorbs all light shined upon it. It emits a spectrum of light that depends upon its temperature. The amount of the Sun emits is called the solar constant, or S0. Our Sun energy gets spread over a disk. Now, this is what explains our energy balance equation, which will be explained further on. So the question is, why does it get colder as you move away from the Sun? Now, if I have to give you an example and you have a bonfire, as you sit close to it, you receive the energy, the warmest point of energy, in fact. However, as you move away, the less energy is received. So, in space, it's a vacuum. So this is new evidence. So our hypothesis is that somehow the light gets less as you get further. It's actually wrong. There's something else to this. If you see the Sun from Earth, you see a circle. Therefore, we have pi r squared. The Earth will trace a band around the Sun, and the Sun energy is spread out over that area. The Venus band is much smaller, and Venus also traces a band around the Sun. However, because it has a smaller distance, the energy is less. The solar constant decreases as you go further. Part B of the practical is the reflected sun's light energy and how is it measured. For this, we look at albedo. Albedo is the percentage of solar radiation which is directly reflected. It depends on surface properties. Looking at Earth, it reflects about 30% of incoming solar radiation. Therefore, albedo is equal to 0.30. Looking at this table in front of you, you see soil and forest highlighted in blue, while water and snow is highlighted in pink. This is because soil and forest have low albedos, while water and snow have higher albedos. Looking at the albedo, it has a symbol of alpha. The amount absorbed is equal to 1 minus alpha. Part C of the practical is, how do we measure the total energy emitted by a body such as Earth? And for this, we briefly touch on Wien's law. Wien's law states the relationship between temperature of a black body and the wavelength at which it emits the most light. In conjunction with Wien's law, we look at Stefan Boltzmann's law, which states that the energy irradiated per meter squared is proportional to the fourth temperature, where E is equal to sigma times temperature to the power of 4, where sigma is equal to 5.67 times 10 to the minus 8 watts per meter squared times Kelvin to the power of minus 4. Our temperature is measured in Kelvin. So the Earth as a sphere, despite what flat earthers say that if I continue walking in one direction, I will eventually fall off Earth. Weird. So it irradiates by the Stefan Boltzmann's law in all directions and all over its surface. The surface of a sphere is equal to 4 pi r squared. Part D of the practical is how is the energy received by Earth related to how the energy emitted. For that, we look at the conservation of energy, and your teacher has been going on and on about energy cannot be created or destroyed. She's absolutely correct. Just like how we intake food and ingest, it's a very similar process. Therefore, energies in a system remain constant. Therefore, the continuous absorption of sunlight leads to an increase in temperature. If the temperature of the planet increases by absorption, then the rate at which it radiates heat into space also increases. Therefore, the average temperature of the planet remains constant. We can then say that the incoming radiation is equal to our net outgoing radiation. Part E is the climax. We use everything we have just learned to set up an equation for the Earth energy balance. So let's balance the energy box. Yellow is represented by our incoming solar radiation towards the Earth. Our disk area of Earth is pi r squared multiplied by our solar constant, which is S0, multiplied by 1 minus albedo, which is our reflected. All of that is equal to our sphere surface of 4 pi r squared multiplied to the amount of heat radiated, which is Stefan Boltzmann's law, which is sigma times temperature, all to the power of 4. So energy received is equal to our energy lost. So we have to rearrange that daunting equation we've just seen. We see that temperature is equal to 1 minus albedo multiplied by S0, which is divided by 4 sigma, all that to the power of quarter. This relates the intensity of solar radiation at the surface to the temperature of a planet. If we plug in the numbers for Earth, we see that the irradiance flux of S0 is equal to 1360 watts per meter squared. Albedo, which I've showed you in the beginning, is equal to 0.3. And using Stefan's constant of sigma, we have 5.6704 as a value. The temperature of Earth as a model, calculating its effective temperature, is equal to minus 18 degrees Celsius. Imagine living in that. So, as represented, our solid circles represent our observed temperatures, as we have seen Venus really hot and Mars really cold. Our dotted circles represent our calculated effective temperatures. Now this is very weird because looking at Venus, it's much colder than it is now. The arrows between the circles represent our differences. So Venus is much colder, Mars is colder than it is now, and Earth falls below our x-axis of minus 18 degrees Celsius. This is very weird. So, going back to our hypothesis, which we said was the distance from the Sun alone is not accountable for the right temperature on Earth. Our hypothesis was just an assumption. So how does all of this link to South Africa? Well, on the east coast of South Africa, we have our warm Mozambique current, and on the west coast, we have our cold Benguela current. So South Africa is one of the countries that received two types of ocean temperatures. So if I go to Cape Town, the beaches there are really cold, but if I go to Durban, it's really warm. And if I go to East London, I guess it's just right. Also, South Africa is one of the countries that receive rainfall in summer and winter, whilst other countries only receive in summer, others only receive in winter. Also, South Africa has an area where they receive no rainfall at all, and this is what makes it good for astronomy, and this is why South Africa built the SKA. So in conclusion, we can see that the right distance and right tint color leads us to a step closer to habitable Earth. Albedo was touched upon in conjunction with the Wien's law and Stefan Boltzmann's law, and we looked at the conservation of energy, and we have figured out that Earth is just right. Look forward to the next lecture on light and air. Thank you.